Hello friends, welcome to Science Team. In today's lecture, we will discuss a few of the thought experiments which lead to the special theory of relativity. So the story begins with Albert Einstein. He used to work in the Swiss patent office and his main work was the electrical and mechanical synchronization of time. And there he observed some strange phenomena and a strange relation between space and time, and he found that this is not similar with the Galilean transformation equations, and he thought that we require some different kind of transformation for the Maxwell equations to be invariant in those transformations. So we will come on those types of transformation in our coming lectures, but in the today's lecture we will discuss the two main conclusions which Einstein arrived by some thought experiment, and the first of them was the time dilation and the second is the length contraction. So let's start with time dilation. So to understand time dilation, just consider that there is a platform, and on the platform there is a train which is moving on the platform, and at its bottom there is a source of light at point A. It emits a straight beam of light, and there is a mirror there, and it reflects at point B and returns back, and there is a detector which can detect that the light has returned back, and there is an observer. We are calling this frame as S prime frame, and also the observer is S prime, and there is another observer outside the train, and it is at rest with respect to the platform. So this train is moving in forward direction with some speed v. It's moving with a constant velocity v in a straight line. So for the observer in S prime frame, he will calculate, he want to calculate the time taken by the beam of light from going to A to B, A to B, and then B to A again. So before we proceed further, we will write the postulate of Einstein. The main postulate of one of the two postulates of a special theory of relativity was that the speed of light is constant in all directions. So just assume that speed of light is constant in all directions, and this speed c is equal to 3 into 10 to the power 8 meters per second. So for S prime observer, the time taken is delta t prime, and this will be equal to AB plus BA divided by the speed of light. You know that AB and BA are same, so this is equal to 2AB by C. Now for the observer in the rest frame, the S frame, he will notice that the light starts from this A point and goes to this B point, because as the light ray goes from A to B, the train moves. So this point has moved a certain distance for this S observer, and when the light returns, the ray returns from B to A, the train has again moved by some distance. Since this speed is constant, so it is moving with these two distances must be same. So this is B point, consider that this is C point and this is D point. So you can see how the two observers see differently. For the S prime observer, all the 3 points are same. A, D and C points are same, and for S observer these events happen, these events of emission of light and then detection of light. So these events, emission and reception of the light, is happening at two different places in space for this S observer, but for S prime observer all these two events are happening at the same point in space. So in this way the two observers see different things. So now this distance is given by D equals V into, now this is what seen by the S observer, so he will multiply it by delta T. This distance is V into delta T. We will come on it later. So now we will calculate this. You know that BD and AB are same distances. So we will calculate BD. So BD equals, from Pythagoras theorem you can say that BD equals AB square minus AD square. You have AD square plus this BD square equals AB square, and from that we can calculate, write this. So we have BD, so we will put this value. Now this BD and the problem is that we should call it A prime and B prime better, so that this AB and that AB should be a different kind of thing. So you can say that this A prime B prime equals this BD. So we will replace this A prime B prime by BD. This is twice BD upon C. So you can write it as square root of AB square minus AD square upon C, and there is a twice. So we have calculated delta T prime, and we can also calculate the delta T. So delta T is AB plus this BC upon AB plus BC divided by your velocity of light. Now AB and BC are same, so we can write as 2AB upon C. So now we have delta T and delta T prime. So we will find the ratio between two. So now we will find the ratio between the delta T prime and delta T. So this will be equal to twice of square root of AB square minus AD square divided by C this is divided by this quantity twice AB upon C. So this C will cancel out and 2 will be also cancel out, and you will get square root of AB square minus AD square upon AB. Now we can put this AB inside the root, so you will get AB square minus AD square upon AB square, which will be equal to square root of 1 minus AD upon AB whole square. Now for the observer in S frame, the light has traveled a distance AB, and in the same time interval the train has moved a distance AD. So this distance is moved by some time which must be delta t by 2. So this distance would be equal to V into delta t by 2, and this distance would be equal to C into delta t by 2. So if you find the ratio between So if you find the ratio between AD and AB, you will get AD equals V into delta t by 2 and AB is C into delta t by 2. So this is the distance observed by the S observer, and this is the distance moved by light for the S observer. Both are for the same observer. So this will be cancelled out and you will get V upon C. So when we put this, we will get delta t prime upon delta t equals square root 1 minus, we have AD by AB equals V by C. So we will put it there, V upon C whole square. Now sometimes we call V by C as beta. So we have delta t prime equals delta t into square root of 1 minus beta square. So this formula is called the time dilation formula. So what we have noticed, that the time interval observed by the observer inside the train is time interval observed by the observer outside the train rest at the platform multiplied with some factor, and this factor must be less than 1 because V by C is less than 1, and for many cases, practical cases, this is much less than 1. But just consider that V is less than 1, so this square root quantity is always going to be less than 1. So this time delta t prime must be less than this delta t. So this is said as moving clocks run slow, and this fact is called as the effect of time dilation. So time dilates, that is the time elapsed is measured to be smaller in a moving frame, or you can say that the rate of elapsing of time is slow. Time elapses in a slow manner in a moving frame. So this is called the time dilation. Now we will come to the length contraction. So length contraction. So as the name suggests, it means that the length is shorter for a moving observer. A moving observer notices that the length has been shortened by some amount. So we will see it by another example. So consider that there is a train which is moving on a platform. So this train is moving with some speed v, and there is an observer inside the train S prime, and there is another observer S outside the train. This platform has a length L. So this observer notices that this train comes and then is moving with some velocity v, which is constant. So the time taken by the train to cross this platform will be delta t equals L upon v, or you can simply say that L equals delta v times delta t. This is the time measured by this S observer. Now for the observer who is inside the train, he will say that the time is dilated. So he will notice that delta t prime is equal to delta t from the formula of time dilation. This is equal to delta t times 1 minus beta square, which is equal to delta t into 1 minus v square upon c square. So the time, they will not agree upon the time taken by the train to cross. For this, the time taken is delta t, and for this S prime observer, the time will be somewhat less. So he will calculate that the length of the platform is L prime, and that L prime will be equal to the speed. Both will say that, he will say that S observer is going in backward direction with a speed v, so he will say that with respect to S, I must be moving with some speed v. So they will agree on the speed of the train, except for the direction. He will say that you are moving in backward direction, but he will tell that you are moving in forward direction with the same velocity, with the same speed. So L prime will be equal to v into delta t prime. So this will be equal to v into delta t times 1 minus v square upon c square. So now you can see that this v into delta t is given by this L. So we will replace this by L times 1 minus v square upon c square. So we have this new formula. For the S observer, the length is L, and for the S prime observer who is moving in with some speed v in a straight line, he will notice that the length of the platform is not L, but it is L prime, which is L times 1 minus v square upon c square. But this quantity is the quantity in square root is less than 1. So L prime must be less than L. So depending on the speed with which the train is moving, the length will appear to be shorter. If there is some train which is moving with a velocity of light, then c square upon c square will be equal to 1, and 1 minus 1 equals to 0. So the length of the platform must be 0, because this term goes to 0. This 1 minus v square upon c square term tends to 0, as we have v tends to c. So for someone moving with a speed of light, these lengths will be 0. The length of the platform will be 0. And similarly for the time dilation effect, delta t prime equals delta t times square root 1 minus v square upon c square. If v equals c, as v approaches c, this term approaches to 0, so delta t prime becomes 0, approaches to 0. So as v approaches c, this implies delta t prime approaches 0. So for an observer who is moving with the speed of light, he will notice that in his frame the time has stopped elapsing. So it will be, so time will be, he will notice that no events are happening and time is not elapsing, and the clock will measure that no time has elapsed. So this was the strange thing that Einstein formulated with his thought experiments. But for these two formulas of length contraction and time dilation to work, the assumption that the speed of light is constant everywhere must hold. Otherwise, these two formulas will not work. So the remaining work was to prove that the light always moves with the same velocity, and nothing can move faster than the speed of light. So this thing was established after Michelson's Morley experiment, but Einstein was a pure theorist and he didn't needed that experiment. He, by intuition, he arrived on the conclusion that for Maxwell's theory of electromagnetic radiation to work, the speed of light must be constant and nothing can move faster than the speed of light. So we will see this in our coming lectures. So please like our video, share our video, and if you have any question then you can ask in the comment section, and thanks for watching.